So, as we know already, let's see, I'll write this guy up. So, definition for displacement, the old hat. Delta X, final position minus initial position. Units are meters. Typically, you can convert from different types of meters, centimeters, nanometers, etc. So displacement different than distance, because distance is just a number. The displacement is a vector. It has a number and a direction. So you could have a displacement of 5 meters. This is an understood plus, 5 meters to the east, west, north, south, all that good stuff. Displacement. Okay. Average velocity. And average is, it's just a kind of a placeholder term. It's just the velocity between 2 points, 2 points of position divided by 2 points in time. It is what you're definitely traveling, well, on average in a trip. But we know that at any moment in that trip, you can be traveling at a velocity greater or less than the average. And the average is just final and initial. That's all you care about. And the instantaneous, okay, I could be doing 500 meters per second at some point in between the final and initial, but the average is like 200, So, again, we've seen this all in all. Delta X over delta T, and typically, we don't write the AVG because we understand it's average when we have this nomenclature here. Average speed is just, distance over time, not displacement. As that would come up at any time, perhaps. Average speed. So the average d over delta t. Well, this is distance, and this, of course, was displacement between 2 points. Of course, instantaneous velocity, we could have a position time graph that gets kind of funky looking, quadratic or otherwise. We could have a curve like this, and we try to take, well, what's the velocity at this point? Oh, tangent line. Okay, it's the velocity at this interval. The time interval is squeezing down to 0. The limit as t goes to 0, the velocity is bam. It's the slope at that point, instantaneous velocity. And the rudiments in and out of limits, so we're just doing it for our purposes. The context is that this is the velocity at that moment in time. So, and of course, if we're just talking about x-axis, y-axis, z-axis, whatever it is, we'll just use the equation that we have. The limit as t goes to 0, your velocity will be blank, right? And then, of course, in calculus nomenclature, same thing, dx dt. I don't know if you can hear that plane overhead, but I'll wait. Okay. Yeah. See you later. So, and then the same goes for average and instantaneous acceleration, the same logic. Okay, so we have, A average, delta V over delta T, and that is our equation for average velocity, final velocity minus initial, T final minus T initial. And of course, it was understood. I have my mouse on me today. X final minus X initial, T final minus T initial. Sorry about that. Okay. This should be as easy as third grade math now, okay? For third graders, or, you know. So instantaneous acceleration, acceleration at a moment in time. You're taking a snapshot at that instant. Okay, what is it? I'm making an observation. I can know where my position is, but I don't know where my momentum is at that moment in time. Same kind of deal. Instantaneous acceleration is the limit as your delta t goes to 0, your time interval is squeezed to that moment, that instantaneous time frame, delta v over delta t, dv dt, same. Yes, technically it's a time interval because the t final t initial is squeezing down to basically nothing. It's getting closer and closer to 0, but not quite 0. That is the point at which you can find your instantaneous velocity, instantaneous acceleration. From a VT graph, in this case, say that you arbitrarily had a VT deal. Oh, I want to find the velocity or acceleration at that moment. The time interval is squeezed, it's getting closer and closer to 0. I can find my acceleration at that point. Simple. What is the slope of the line at that point? What's the tangent line reading? What is the slope of this line? Whatever that slope is, that gives you the acceleration at that moment. We've done this, we've seen it. Hopefully that's all right. Just going over that again. Now again, particle under constant velocity and leading on to the kinematics equations, everything is derived from a VT graph. That way we can get 2 equations for velocity final and 2 equations for displacement, all from a VT function. We can go forward, take the slope of a VT and get the acceleration, go backwards and get the positions or displacements, right? And then from there, we can derive all of the equations for kinematics. So again, starting off with particle under constant velocity. Okay, it's basically the average velocity equation, delta x over delta t. And then, of course, if we want to find the final position, delta x equals v delta t, and this is x final minus x initial, v t final minus t initial. And then if we want to find the final position from an xt graph, it's going to be xi plus v t final minus t initial, or just v delta t. So that's, again, going back over that sort of business. It's like our first kinematics equation, or a motion equation to find your final position without need for the acceleration term in this equation. So that we have that. And of course, constant speed, it involves the average speed equation, d over delta t. We know that speed is different than velocity. Speed is the magnitude of your velocity. If you have velocity plus 5 meters per second, well, the absolute value is your speed. The whole thing is your velocity, because as you're in your car going at 5 meters per second, you're looking out the window. So you're actually a closed system of velocity. You know where you're going and you know how fast you're going. So that's the velocity. And the speedometer, okay, obviously measures your speed, and it's just a number. So particle under constant acceleration, the kinematics equations, right? So let me go on my typical order. Delta x, 1/2 v final plus vi delta t. That's just the area of that right triangle of your VT graph. 1/2 base times height. And then we have delta x equals VIT plus 1/2 a delta t squared. I'm just going to say t squared. That's finding delta x, displacement, when you know velocity, time, acceleration. Okay, and then final velocity, VI plus a delta t, or I'm just going to say AT. We're used to seeing the t's by now. And then V final squared equals VI squared plus 2a delta x. Okay, so that's just a reprise of you know, everything we've seen equation-wise in chapter 2. Also, the business of things having acceleration versus deceleration, or slowing down, speeding up, slowing down. So if your velocity and your acceleration are in the same directions, constant acceleration, that is our context of everything, then this object is speeding up. So constant A, even though graphically this looks like this, the slope is constant, it's steadily getting higher and higher down here too. It's just in the negative direction. Okay, this is accelerating. Accelerating or speeding up. Right? And then opposite, if the velocity acceleration vectors are in opposite directions, we are slowing down. Right? I really need to do that, but you know, you can see my whiteboard stuff. Anyway, so then if I'm slowing down, I'm going, whoa, large to smaller, smaller, and then, oops, my acceleration goes the other way. I'm putting on the brakes. Okay, opposite directions, slowing down. So, you know, you have a negative slope in DT. You have a situation like this. Then in AT, it's going to be negative constant. Something like that. Then obviously, if we have a constant velocity, there's no AT at all, no acceleration. So again, as a reprise for for Thursday, I guess I'll see you next. Let's do chapter 2 and chapter 3 conceptual questions, just as a review. Since we're here, let's take advantage of that of this time. So moving on to chapter 3, the nature of vectors, how do we graphically add vectors? It's basically the abstraction or the method of vector addition, subtraction, and all that stuff, as a precursor to all of our projectile motion stuff and unit vector stuff in chapter 4. So let's go over here. So chapter 3 deals with vectors. Some arbitrary vector R is the sum of vectors A and B. You don't add A and B because they're vectors, and so you have to take care of their parts. And the basic way that you can find the magnitude or the size of vector R is to use the Pythagorean theorem to figure out what the value of R is. So A plus B is just, so say R is made of A and B. Just a way of looking at that equation. Take out a technical jargon because you don't always have to use those terms. All right, so the magnitude A squared plus B squared, it is like your Pythagorean theorem for right triangles, same thing, because the vector R is going to be a right triangular sum of the parts of A and B. So for example, so R is square root of A squared plus B squared. R is A plus B. So we know that by definition up top, Rx is going to be equal to AX plus BX. Ry is AY plus BY. And this is a linear combination of the parts. Can I do this? And then that just becomes A plus B. And so that's what we've done as just a background to dealing with questions in forces, projectile motion, and other kinematics equations that involve their parts. So R is made up of X and Y, Rx, Ry, A is AX plus AY, B is BX plus BY, and R is the sum total of A, which is subsumed. These parts are in A and these parts are in B. So just a little bit about that. We can also say that the Rx, or in unit vector notation, Rx is Ri, which is made up of all of the i's, in A and B. All right, AI plus BI, this is a unit vector that it really has no physical significance. It's just a pointer to let you know that you're along the x-axis in the Cartesian coordinate system, because in another coordinate system, like the spherical coordinate system, I hat becomes R, theta or phi. It's just a marker, if anything. And then this is J hat. That's going to be AJ hat. And then that's going to be, of course, A plus B. It's the same thing. And you can get even fancier if you really understand that it's AX I hat. This is kind of redundant, but as long as you get the idea. So that was the stipulation of chapter 3. So I would say that we would let's do the conceptual questions for both 2 and 3. No more than that for next time, and we'll come back and talk about more equations. We'll talk about the rest of the equations for the other chapters, and success of, so like I mentioned a time ago, that your homework now will just be conceptual questions, and then we'll have the in-class practice multiple choice and FRQs. So any questions so far? This good stuff. Chapter 4. Yeah, I think the biggest idea from chapter 4 is projectile motion. We'll come back to that. Projectile motion, kinematics equations in 2 dimensions, and all of the different derivations. Like, so we can have delta x equals vi cosine delta t, and we can derive the range equation. So in the time that remains, I guess I'll write some of those guys up. Section 4.3. So projectile motion. We know that v, vector v, if we have path that looks like this, and we know that successive velocities at each of these points, all of these different instances, will have tangent lines that look something like this. And then if this is a velocity at this point, which is the slope of the curve at this point, well, this velocity v is going to be comprised of an x component and a y component. And then on the way back down, the slope at this point is going to be, well, negative slope, right? And it's going to make made up of the Vy, negative Vy, and Vx. And gravity is constant downward. And so the y component is the component that's only changing. So at this point, not to scale up, obviously, but Vx will be constant and Vy will get smaller and smaller until at the very top here, the velocity in the y direction is 0, but we still have a component in the x direction that's going to propel this projectile forward. So it just doesn't stop here and fall down. So this velocity made up of x component and y component, even z component, just 3 dimensions. So that's what we have here. It's made up of those two guys. And we'll just continue on. This would be negative Vy, this would be x, constant. Why? Because gravity doesn't affect the x-axis. This is the composition of V. And then obviously Vx, with respect to this angle theta here, is going to be V, we'll just say Vi cosine theta. And then Vy will be Vi sine. Then over here, likewise, V final is going to be V final x. So I should say V final cosine theta. But we know that all the x components are going to be constant. Vxi, Vxf equals Vx is a constant because nothing affects the velocity in the x direction. So Vfy is Vf sine theta. So they're the parts in terms of trigonometry. So be our parts. So again, theta is over there. So we have kinematics equation, basically a fifth kinematics equation that deals with the range, the horizontal range. So we could, there's 4 equations that deal with the y-axis. Then there's another one for the x, delta x, Vi cosine theta delta t. And we've done a couple of problems where we know that the delta x, or the range, can be rewritten as Vi squared sine 2 theta over g. And then we also have a maximum height. So this will be the horizontal displacement or range equation. And then our maximum height, we can use the delta y equation in terms of 1/2 gt squared to derive this equation for our maximum height, which we've done before a long time ago. This will be just a quicker way to find the maximum height of a projectile when you know the angle, initial speed, of course, gravity. So just a little bit on the projectiles. In a symmetric situation, where this is y versus t, or y versus x, actually, technically speaking. The time it takes to go up is equal to the time it takes to go down. And the initial velocity will be equal to negative v final, at least in the y direction. And they're symmetric and equal to each other. So this is a symmetry problem where these guys are equal to each other. So this y initial here is equal to y final, which is equal to 0. So that's for our symmetry. Everything on each side of this parabola is the same. Of course, asymmetric, we can't do that. Just a little blurb on those guys again. Of course, the range equation helps us understand that complementary angles will give us the same distance, same horizontal distance. So, all right, I'll stop there. Continue on Thursday. So I'll be posting up the homework, conceptual questions, chapters 2 and 3, and we'll come back for more equations on Thursday. All right. Okay, if there's no further questions. I don't know if you can hear that.